Welcome to another Mathcast. In this episode, we're going to be taking a look at arc length formulas involving parametric curves. We have two parametric curves here, or at least one parametric curve. The x-coordinate of the curve is e to the t minus t, and the y-coordinate is 4e to the t halves. And this curve drawn out from 0 to 3 is represented in the graph over here. Notice if we look at, for example, t equal to 0, x of 0 is e to the 0 minus 0 or 1. And y at 0 is 4e to the 0 or 4. And so at time 0, we start off at the point 1, 4, which is right here. And so for time equal to 0, we start there and we finish up over here. And if you plug in the values, you get e cubed minus 3 and 4e to the 3 halves is our finishing point, and this is after 3 seconds. So we start off at time 0, and for 3 seconds we follow this parametric equation and it draws out the following curve. And what I want to know is, what is the length of the curve? So let me quickly remind you that when dealing with arc length, we're looking at this ds element, which is the square root of dx squared plus dy squared. We saw this in another video. But for parametric equations, you introduce the parameter t for time, meaning I should divide through this side by, in other words, I should divide both sides by dt. And if I do that, what you'll wind up with is the square root of dx squared over dt squared plus dy squared over dt squared, and then you pull the dt out in front, which comes from multiplying both sides by dt, to bring the dt on this side over. Now we've done this in class, so you should be familiar with this setup. If I just want to take this one step further here, basically I'm going to take x and differentiate with respect to t and then square that, and then do the same thing for the y component. And then I'll be integrating with respect to t, and we know for this particular problem t goes from 0 to 3. So if you put all that together, you should wind up with an arc length integral that goes from 0 to 3 of the square root of, in this case, it's e to the t minus 1 squared. That's what you get if you take the derivative of that. So dx dt for this example is e to the t minus 1. And similarly, dy dt is 2e to the t halves. Notice that you've got the 1/2 term coming out in front there with the chain rule. And so we've got our dy dt term as well. And we're squaring both pieces and integrating with respect to t. So this is the arc length element I'm using for parametric curves, and this is the updated version for this particular curve. All right, if we do a little more work here on the inside, factoring all this out, we'll get e to the 2t minus 2e to the t plus 1. That's from the first term. And then the second term gives 4e to the t. Now, all this is still under the square root. All right, if we do a little work off to the side here, what's underneath the radical at this point is nothing more than e to the 2t plus 2e to the t plus 1. And you may not be familiar with this, but basically I should treat this as if e to the t is taking the place of x in a polynomial. For example, this is nothing more than the polynomial x squared plus 2x plus 1, which is a perfect square and factors nicely into x plus 1 squared. It just so happens, though, that the x for this particular problem is played by the role of e to the t. And so the result is, if I take the integral I'm looking at here, this is the integral from 0 to 3 of the square root of, not x plus 1, but e to the t plus 1 quantity squared dt. Well, that works out rather nicely. I can drop the square. I can drop the square root as well. And then if I continue out the integration, this is e to the t plus t, evaluated from 0 to 3, which gives us a final answer of e cubed plus 3 minus 1, or e cubed plus 2. Now, I encourage you to check this on your own work. It should come out to be the exact same thing, but this is the length of this curve. So the length of this curve is e cubed plus 2. Alright, we're going to take a look at one more video involving arc length, and that is with polar curves. So I encourage you to watch that. Thank you for watching.